Hi, in this video we're going to look at the derivative. We're going to look at the definition of the derivative, look at a little picture of it, and then we'll do an example of finding a derivative using the definition. So let's start off with the function, and it'll need to be a particular type of function, but we won't worry about that right now. We can write, if this limit exists, we can write that the derivative, denoted f prime of x, is equal to the limit as h goes to 0 of f of x plus h minus f of x divided by h. Again, this can be written if the limit does indeed exist for the given x value and the function f. You might notice the part here, f of x plus h minus f of x over h, this part of the limit, or the thing that is being, or the limit is being applied to, is the difference quotient. And that has geometric meaning. Let's review that. So if we have a function f, this blue line, or this blue curve right here, and we have an x value, say x, and x value sometime later, x plus h, we can find the average rate of change of the function by plotting the 2 points. So x comma f of x right here. So it's x in the vertical, f of x horizontal. That point right there on the curve. We have x plus h, so vertical, horizontal, goes over right here. And then those 2 points, we can draw a line through them. And the slope of that line is the average rate of change. We call that line a secant line. Okay. If we, though, take this difference quotient, this average rate of change, and we let h be a smaller value, that is, the distance between x and x plus h is smaller, then this line will move a little bit. And if we keep up making h smaller, in special cases, in certain cases, for the function f and value x, we may get the case where these slopes approach a value. So there's some limit. That value we call the derivative. I've drawn a line here that would be what this limit of secant lines may end up being for this function. If such a thing exists, we call it a tangent line, and the slope of this tangent line is the derivative. So the derivative is you can consider it the instantaneous rate of change of the function. You can consider it the slope of the tangent line at a given point. Right. Applications of this will be forthcoming in the coming sections, and then again in Chapter 4. Let's take a look at this definition applied to a particular function. So we're going to find f prime of x, and we're going to use the definition that we have over here for f of x equals x squared minus 3x. Okay, so we know we have to find the limit of the difference quotient for this function. So let's set this up. Work out the difference quotient, and then we'll apply the limit. All right, so we'll start with, first off, we want the derivative, so we'll start off with f prime of x equals the limit as h goes to 0 of the difference quotient right here. So we want f of x plus h. So that means we take x plus h and evaluate it in our function. So wherever we see x, we will replace it with x plus h. Okay, so we have x plus h, quantity squared, minus 3 times x plus h. That takes care of this part. Then we want to subtract f of x. So subtract, parentheses, f of x, so x squared minus 3x. And then all of this is divided by h. Okay, so we have f of x plus h minus f of x divided by h. All right, let's then simplify this. We can't immediately take the limit as h goes to 0 because we have an h in the denominator. That would cause division by 0, which would give us, which we cannot do, of course. And we'd want to simplify this to make sure that we're not ignoring any particular value that this could be. In other words, we don't want to just say this limit doesn't exist at this point. We want to simplify it and see if we can find a value for it or an expression for it. All right, x plus h squared is going to be x squared plus 2xh plus h squared, multiplying out this x plus h squared. Then we'll take this negative 3 and distribute it. So we have negative 3x minus 3h. And then we'll distribute this minus sign into the f of x. So minus x squared plus 3x. All that divided by h. Okay. Now let's see if there's anything in the numerator that we can simplify. And we can indeed see some simplification here. We've got a minus x squared and a plus x squared. Get rid of those. Minus 3x and a plus 3x. Get rid of those. So that leaves 2xh plus h squared minus 3h in the numerator. So limit, h goes to 0. We haven't applied the limit yet, so every time we write a new line, we'll have to start with the limit here until we do that. So, see, 2xh plus h squared minus 3h all over h. All right, if we look at the numerator, we'll see that each has a common factor of h. So we'll divide h into each one. So again, limit, h goes to 0, 2x plus h minus 3. And now this resulting expression here is just a polynomial in h. This 2x does not have an h, so it's treated as a constant. And of course, the limit of a constant is a constant. So we have 2x. The limit as h goes to 0. Well, h is going to 0, so that's plus 0. And then negative 3 is also a constant, so that is stay the same. So we have 2x plus 0 minus 3. So the answer is 2x minus 3. So the derivative of x squared minus 3x is 2x minus 3.